Hello and welcome to the webinar on lube and hydraulics oil filter testing. My name is Kal Farouk with the Scientific and Laboratory Services Group of Paul Corporation at their Port Washington, New York facility. Before we start, please note the slide can be enlarged by hitting on the screen icon on the upper right hand corner of the slide. If you have any questions during the presentation, there is a Q&A icon at the bottom left of the page. Please click on this icon and type in your question. I will try to answer them after the presentation is over. Here is the outline of my presentation. First, I will discuss the need for the test methods that can be trusted to provide accurate information about filter performance, the filters that we depend on to protect expensive machinery and processes. Next, I will talk about in some detail the popular multi-pass test and its limitations. Then I will talk about the relatively new test method that is designed to overcome some of the limitations of the multi-pass test, so it can provide more insight into a filter's expected performance under more challenging conditions. Then I will go over some of the test data, followed by the conclusions. In order to make an informed decision about which filter to use, one needs to understand and trust the information they are provided about the filter's performance. Reputable quality filter makers always use test methods from standards organizations such as ISO, SAE, and FPA to test and rate their filters. Some filter makers rate their filters as nominal for a micron size. Since there is no clear definition for a nominal rating or a test method to come up with this rating, there is no way to compare its performance with another filter. It is therefore not a good idea to select a filter based on its nominal rating. The standards organizations such as ISO are run by subject matter experts from the industry. They work hard to make sure the test methods they are writing and approving provides meaningful results and meet the highest technical standards. Thus, the use of these approved test methods ensure consistency in how filters from different manufacturers are tested in an unbiased manner. This is important for making a fair comparison between the filters. The multi-pass test method that was first released by ISO, the International Standards Organization, back in 1981, has been and still is a widely used filter testing method. The method was updated in 1999 and again in 2008, and currently has the designation of ISO 16889. In the next slide, I'll show more details about the multi-pass test. Here is a simplified diagram of the multi-pass test circuit. The test fluid, which is a mineral-based 15 centi-stokes hydraulic oil, is pumped through the test filter and back into the reservoir. The test fluid is spiked with a silica-based test dust, which has a certain particle size distribution. The concentration of the test dust is kept at a level so that the filter reaches the target differential pressure. That is, it gets plugged in about an hour or so. Oil samples are taken up and downstream of the test filter for the counting of the particles to measure the filter's removal efficiency. The particles that are not captured by the filter go back into the reservoir and come back for another pass through the filter, hence the term multi-pass, since the uncaptured dirt makes multiple passes through the filter. The oil samples taken up and downstream of the test filter are counted by online light scattering type particle counters throughout the test at set intervals, usually every 60 seconds. The counts are then used to calculate the removal efficiency for each sample that was taken and to calculate the average removal efficiency at the end of the test. This is a simple explanation of tests. There are many other details that are outlined in the ISO 16889 document. Next plot, I'll show the multi-pass test data. This plot shows particle removal efficiency, or the filtration ratio, also called the beta ratio, for 5 different grades of filters made by Pall Corporation. The leftmost black line represents the finest grade, which has filtration ratio of 1000 for particles 3 microns C and larger. The subscript C refers to the particle counter calibration method. Pall rates its filters for beta ratio of 1000, which means 99.9% removal efficiency at the rated micron size. This plot shows filtration ratio at sizes other than the rated size. Most filter vendors do not provide this level of detail. They provide only 1 micron size and the corresponding beta ratio. So when a user selects a filter based on its micron rating, usually a single number based on the multi-pass test, it does not provide any information about the filter performance at other particle sizes. The multi-pass test, although a reliable test method that has been in use for decades for assessing and comparing filter performance, has limitations. The main ones are that the test requires very high dust injection or loading rate compared to what happens in real life. And the reason for high dirt injection during the test is to be able to complete the test in a reasonable amount of time, which is usually an hour. The dust injection can range from 1,000 to as high as 10,000 times the rate at which the filter experiences in the real life application. The downside of high dust injection rate is that it tends to mask the deficiencies in filter performance. Secondly, the test uses a constant flow rate, which is not the case in real life. Especially in hydraulic systems, the flow varies widely. Even in loop systems, there can be frequent start and stops, resulting in flow changes. Thirdly, as I mentioned before, the multi-pass test reports the average removal efficiency. Any performance degradation, which usually happens towards the end of the test when the filter is under highest stress, is not apparent from the filter rating, which is based on the average performance. These limitations of the multi-pass test prevents the evaluation of the filters under conditions that are closer to real life found in most industrial systems. Filter users and makers realized the limitations of the multi-pass test and saw the need for a more challenging test for filter performance. Pall Corporation, being a leader in the filtration industry, developed an in-house test that was called the Cyclic Stabilization Test, or the CST test. I mentioned earlier, there was a realization in the industry about the limitations of the multi-pass test and the need for a test that is closer to real-life conditions. Filter performance under cyclic flow as opposed to constant flow that the multi-pass test uses was of interest. The Pall Cyclic Stabilization Test is based on cyclic flow. This test was developed by Pall in the late 1990s. Society of Automotive Engineers, or SAE, they have a committee, A6C1 committee, that deals with hydraulic filters, was also interested in a test method based on cyclic flow. Pall, being a member of the committee, proposed its CST test to the committee. Along with Pall, there was another test that was proposed to the committee called the Dynamic Filter Efficiency, or DFE test. After a long process, spanning almost 5 years that included thorough discussion among industry experts, testing and verification between labs. The SAE committee adopted Paul's CST method with minor modification. This method is now called SAE ARP 4205. The International Standards Organization, or ISO, that developed the multi-pass test is also working on a cyclic flow test method. They call it ISO 23369. This method is still under development. The ISO committee, of which Paul is also a member, has accepted many features of the SAE method, including the cycling rate of the flow. Before I get into more details about the CST test, here are a few details about the DFE test, the other cyclic flow test that I could find on the web. Since this test is not sanctioned by any standards body, a copy of the detailed test procedure is not available. This test was developed by Scientific Services Inc., or SSI. According to SSI, the test is designed to measure dirt released by the filter due to flow cycling. The test uses flow cycling between full and 50% of the full flow for 3 minutes each. This translates to a cycling rate which is way slower than most real-world hydraulic applications. To my knowledge, there is only one filter company that uses this test method to market their filters, calling them DFE rated filters. SSI is the only lab that is known to run this test. Since the details and the procedure and test equipment are not publicly available, no other lab is in a position to run this test. Here is the test circuit for the DFE test that I downloaded from the SSI website. It is similar to the multi-pass test circuit, except that it uses a solenoid controlled directional valve downstream of the filter that is cycled to vary the flow between 100% and 50% through the test filter. Now getting back to the SAE cyclic flow test method, which is based on the Paul CST method. The flow cycles from full flow down to 25% of the full flow at a cycling rate of 0.1 hertz, which means 5 seconds of full flow and 5 seconds of 25% of the full flow. This cycling rate is a lot closer to real-life conditions found in many applications, and the drop to 25% of the full flow is more challenging in the sense that a drop to 25% induces more stress on filter media compared to a drop to 50%. This test uses a finer grade of the silica test dust called ISO A2 fine test dust, compared to the multi-pass test and the DFE test that uses a coarser grade, which is ISO A3 medium test dust. Experts agree that the coarser test dust is more prone to form a cake under certain conditions on the filter during the test. This caking of the test dust tends to artificially enhance the performance as the cake itself acts as a filter. As in the multi-pass test, this test requires sampling up and downstream of the test filter at set intervals and provides a micron rating in addition to other information, as we will see later. A unique feature of this test is that dirt injection is stopped after the differential pressure across the test filter reaches 22.5% of the target differential pressure, which, as you can imagine, will happen soon after the start of the test. This is when the filter is pretty much new and not loaded, hence not under much stress. Similarly, the injection is stopped when the differential pressure reaches 80% of the target value. This is close to the end of the test, when the filter is almost fully loaded and under high stress due to the high differential pressure. These dirt injection stoppages happen while the flow is constantly being cycled and up and downstream oil samples are being taken. As the injection is stopped, the filter cleans up the test stand as the fluid goes through the filter, as it happens in a real system. This goes on for 30 minutes. The particle counts and the final cleanliness level of the test fluid at the end of the 30 minutes period is recorded. This provides important information about the filter performance. The cleanup allows contamination level of the test fluid to approach very low levels, similar to what we see in real-life conditions. And unlike the multi-pass and the DFE tests, where the dust injection rates can be as high as 10,000 times the real-world conditions, the final cleanliness reported in terms of ISO 4406 cleanliness codes provides information about filter performance at 3 particle size ranges, which are 4 micron, 6 micron, and 14 micron C. The SAE cyclic flow test method offered several advantages over the multi-pass test and also the DFE test method. The plot showing only the 5 micron size for clarity illustrates what I said previously, that the dirt injection is stopped at 2.5% of the target delta P and also at 80% of the target delta P. The plot shows the system cleanup after the injection is stopped. Typically, the filters are able to clean up better, that is to lower counts, at 2.5% delta P compared to the 80% delta P when the filter is under greater stress. Therefore, a inferior quality filter will be more easily identified under the cyclic flow and pressure conditions of the test. As the dirt injection is stopped, the filter is challenged with decreasing levels of dirt, which is closer to real-life levels. This helps bring out the true removal efficiency of the filter in close to real-life conditions. The cleanliness level of the test circuit the filter is able to achieve is a key output of this test. It gives a good idea to a system designer what cleanliness the filter can achieve. This is more meaningful information than a single micron rating based on the multi-pass test and the DFE test method. Since the SAE RP4205 and the DFE are the only 2 cyclic flow test methods that are currently known, let's see how these 2 tests compare. First major difference is the flow cycling rate. In the case of the DFE test, it is 36 times lower than the SAE test. Hence, it is more gentler on the filter and lots slower than what a typical industrial application would experience. The next major difference is the test dust. Isofine test dust used by the SAE test is more challenging for fine filters as it has more finer particles, and unlike the isomedium test dust used by the DFE method, it does not tend to form cake on the filter, which can lead to higher removal efficiency by virtue of the cake and not the filter media itself. The DFE test is not approved by any standards organization, and no detailed test procedures available that can allow an independent lab to design and conduct the test. SSI is the only known lab in the world that can run this test. On the other hand, SAE procedure is published and have enough details for a lab anywhere in the world to construct the test stand and conduct the test. Now let's look at some of the test data. This table shows the results for filters from 8 different manufacturers that were rated by the multi-pass test method as 5 micron CS beta ratio of 1000. But when tested under cyclic flow per the SAE method, the performance varied by a wide margin, as you can see. For example, the oil filtered by the filter from manufacturer number 1 had roughly 32 times lower number of 4 micron and larger size particles compared to the filter from manufacturer number 8. That is a huge difference in performance for two filters that were rated as identical by the multi-pass test. This data shows how well the SAE test can differentiate between filters that were rated as equals by the multi-pass test. Here is some more test data for filters from two manufacturers tested by the multi-pass test. These filters are made with 7 micron rated anti-static media. Anti-static media refers to the filter media used for the mitigation of the static charge generation, a common problem with mineral-based turbine oils when using a standard glass fiber media. As the test data shows, the Paul filter had beta ratio of 1190 as the rated 7 micron C size versus 304 for the brand H, almost 4 times higher removal efficiency for the Paul filter. Now looking at the same two filters tested per the SAE ARP 4205 method, the number of particles greater than 7 micron per ml that the two filters were able to achieve in the test circuit at the point of 80% loading, it was 43 times lower for the Paul filter compared to the brand H. The plot also shows a marked difference in the speed of the cleanup and the level of cleanup, as you can see from the plots. The test captured similar data at 6 size ranges. Here I'm showing only one size for clarity. The trend was similar for all other sizes. This graph illustrates the same data as in the previous slide. It is important to note these numbers represent the filter performance at its worst, when the filter is loaded with dirt towards the end of its service life and is being subjected to cyclic flow, which induces cyclic stresses, of course, fluxes the filter media. The number of 7 micron particles per 100 ml shown are upstream of the filter. This shows how well the SAE test method, cyclic test method, can differentiate between similarly rated filters. So here is what we can conclude from the presentation. To make informed decision when selecting filters, trust only the industry-sanctioned test methods. These test methods are put together by filtration experts from across the industry with the sole purpose of designing a test that is accurate, repeatable, and reproducible, and provides meaningful, usable data. These industry experts, mostly volunteers, work diligently to write these standards so that a level playing field is provided for the manufacturers to test their filters and users are able to make an informed decision. In this presentation, we also learned about the multi-pass test method and its limitations. We also learned why testing for filter performance under cyclic flow is more realistic and better able to distinguish a good filter from a mediocre one. Currently, SAE ARP 4205 is the only industry-sanctioned cyclic flow test method. This test is based on Paul cyclic stabilization or CST test and provides meaningful information about filter performance under conditions that are closer to real life. Filter plays an important role in the service life and reliability of the hydraulic and lubricated machinery. It is therefore important to rely only on filters that are rated by industry-sanctioned standard test methods and not by non-standard tests. Using the nominal rating of a filter without any details about the test method or relying on non-standard tests such as the DFE test invalidates any meaningful comparison between filters. I like to leave you with this quote from the filtration industry's leading trade organization. It summarizes well the gist of my presentation, that the buyers be aware. Do not trust non-standard tests when it comes to selecting filters to protect your expensive equipment and processes. I thank you for your time and attention. I will now try to answer the questions that were submitted during the presentation. If anything comes to mind later, please feel free to get in touch with me at the contact information shown here, and I'll be more than happy to answer any questions. Thank you again. Hi, I have two questions. Number one, you mentioned that the test dust used in the multi-pass test forms a cake that artificially enhances filter performance. Does that mean multi-pass test data is not reliable? What I said was the test dust used in the multi-pass is prone to caking. I have seen it happens many times. Doesn't necessarily mean it happens every time. It happens under certain conditions, and it can be avoided by setting the test parameters correctly, especially the loading rate. The review of full multi-pass test report will show if caking happened. We at Paul discard the test when it happens. The second question was, when will the ISO version of the SAE cyclic flow test be available? The answer is the ISO cyclic flow test 23369 is currently in public comment stage. I am not part of the committee, so I'm not sure when it will be officially released, hopefully soon. But the test document is available to members and several filter makers, and test labs are already referencing it in their literature. I don't see any other questions that popped up. So with this, I thank you again very much for your time and attention. Bye-bye.